Welcome to today's Explainer. I am so excited you're here because today we are taking a seriously fascinating anatomical journey. We're going to trace the body's internal communication network to truly understand neuromuscular disorders. These aren't just localized skeletal injuries, they are disruptions in a highly intricate, interconnected system. By the end of this Explainer, we'll have demystified 5 distinct conditions just by following the electrical pathway right from the top down. Okay, let's dive into this.
Here's our roadmap for today. Removing top-down. First, the relay race. Second, the brain, specifically looking at cerebral palsy. Third, the spinal cord, where we'll cover polio and SMA. Fourth, the junction, focusing on myasthenia gravis. Fifth, the muscles themselves, for muscular dystrophy. And finally, number 6, lived experiences. This isn't just a random list, by the way. It's the actual physical path a nerve impulse takes.
Okay, Section 1, the relay race. Let's look at how healthy movement actually works. To really grasp these disorders, we first need to appreciate the absolute magic of healthy movement. Think of it like a high-speed electrical relay race, and there are 4 crucial steps. Step 1, it all starts in the brain, which sends out an electrical impulse. Step 2, that impulse races down the spinal cord via specialized motor neurons. Step 3, it hits the neuromuscular junction and crosses the gap using chemical messengers. And finally, Step 4, the impulse strikes the muscle fibers, triggering a contraction. Now, a breakdown at literally any single one of these stations, that's what results in a neuromuscular impairment.
Moving on to Section 2. Station 1 on our physical map, the brain, and specifically cerebral palsy or CP. So when damage happens to the brain's motor region early in life, it basically disrupts that very first handoff in our relay race. That's cerebral palsy. Now, the most common presentation here is spasticity. We're talking about stiff, tight muscles that make movements look jerky or rigid. If you're in a classroom, you might spot this through things like persistent toe walking, maybe an unsteady gait, or even speech articulation challenges, which is known as dysarthria. And that's just caused by weakness in the facial and tongue muscles. You might also catch some tremors when the person is reaching for an object.
There's a quote I want to share. The student processes ideas quickly, but physical responses take extra time. This just brilliantly captures the lived experience of motor latency. The brain is firing perfectly fine when it comes to ideas and cognitive speed, right? But translating that into physical movement, that's delayed. On top of that, for someone with CP, just doing something like maintaining balance and sitting upright with a specialized back support, that consumes a massive amount of energy. It often leads to deep physical exhaustion and early afternoon fatigue.
All right, Section 3, we're moving down to the spinal cord. Here we'll look at polio, post-polio syndrome, and spinal muscular atrophy.
So we're traveling further down that anatomical pathway, leaving the brain and entering the spinal cord. Here we run into 2 totally different conditions that both end up damaging crucial motor neurons. First up, poliomyelitis and post-polio syndrome, or PPS. This is actually an acquired viral infection. It often causes asymmetrical muscle weakness, meaning, one leg or arm is significantly more affected than the other, sometimes even decades later. Now, contrast that with spinal muscular atrophy, or SMA. Unlike a virus, SMA is a genetic disease, and it causes severe, progressive muscle wasting. With SMA, you'll see extreme low muscle tone early in life. It often leaves a child completely unable to sit unsupported or even lift their chest. There's a truly fascinating physical reality to consider here, especially for polio and PPS. A person with this condition actually has totally normal sensory perception. They feel heat, cold, a light touch completely normally. But because the motor neurons in the spinal cord are damaged, the muscles simply can't respond to the brain's command to move. On the flip side, with a condition like SMA, the physical weakness is so severe that individuals often can't even lift a textbook. This means they rely heavily on highly sensitive tech accommodations, like eye gaze systems, just to communicate and participate in class.
Next up, Section 4, the junction. Let's talk about myasthenia gravis.
Okay, so we've arrived at the 3rd station of our relay race, the neuromuscular junction. This is where the body's immune system mistakenly goes rogue and attacks its own chemical messengers, specifically the acetylcholine receptors. This literally prevents the electrical signal from crossing the gap to the muscle. A key visual marker for this is ptosis, which is the drooping of one or both eyelids, especially as it gets later in the day. Because of this autoimmune blockade at the junction, you might also notice things like double vision, facial expressions that kind of appear frozen after smiling for a bit, or speech that gets slurred and nasal as a long conversation goes on.
This drastically fluctuating energy is really the hallmark of myasthenia gravis. Morning performance, usually quite strong, because the muscles work relatively well after they've had complete rest. But by the afternoon, fatigue really sets in, and the muscles weaken rapidly during sustained physical activity. This is exactly why a student with MG might need a split test schedule or frequent rest breaks. Extended reading can trigger severe visual and hand fatigue. They literally just need time for their junction's chemical messengers to reset.
Moving on to Section 5, the muscle fibers. Let's dive into muscular dystrophy, or MD.
All right, the final stop on our anatomical journey. The signal has made it all the way from the brain, down the cord, across the junction. But here, the problem lies in the muscle tissue itself. And there's a supercritical distinction we need to make right now. Remember cerebral palsy? That's a non-progressive condition. The initial brain injury is static, it doesn't get worse. Muscular dystrophy, on the other hand, is a group of genetic diseases that are progressive. It gradually worsens over time as the muscle fibers themselves actually degenerate and break down. The huge takeaway here is that someone with MD requires continuous adaptation over time to their environment and their tools, which is totally different from the relatively static physical baseline we see with CP. A really helpful visual anchor that perfectly illustrates muscular dystrophy is Gower's sign. Because the pelvic and thigh muscles get so weak, a child trying to get up from the floor will use their hands to literally walk up their own legs just to push themselves upright. You might also notice frequent falls, a waddle in gait, or calf muscles that look unusually large or swollen. That last one is actually called pseudohypertrophy, and it happens when fat tissue steps in to replace the lost muscle fibers. To ground this in everyday reality, the progressive nature of MD means a person's physical stamina is constantly in flux. For example, diminishing handwriting strength means they need to actively transition from traditional pens over to adaptive keypads or voice-to-text software. It also means that having ergonomic seating isn't just nice to have, it's an absolute must to help manage that loss of physical stamina throughout a long day.
Which brings us to Section 6, Inclusion and Lived Experiences. Let's synthesize these accommodations.
You see, by tracing this electrical pathway all the way from the brain to the muscles, we aren't just learning medical trivia. We're understanding the physiological why, and that is what empowers us to create the exact right accommodations in our classrooms and workplaces. It's actually amazing how neatly our top-down journey maps to these practical solutions. Think about it. Cerebral palsy originates in the brain, presents as spasticity, and requires extended response times. Muscular dystrophy hits the muscle fibers directly, presents with Gower sign, and desperately needs ergonomic seating. Polio and PPS impact the spinal cord, present as asymmetrical limb atrophy, and demand spatial accessibility for mobility aids. Spinal muscular atrophy also damages those spinal motor neurons, resulting in severe low tone, and is supported beautifully by eye gaze technology. And finally, myasthenia gravis attacks the neuromuscular junction, shows up as drooping eyelids, and is best accommodated by morning testing schedules when energy is at its absolute highest.
Cognitive abilities remain completely unaffected. We've spent this entire explainer talking about the physical pathway of movement breaking down, but we have to emphatically remind ourselves at this point. Towering physical barriers do not equate to cognitive barriers. The mind is completely ready and willing. It's just the physical relay race that's hitting some hurdles.
So, that leaves us with one final, incredibly vital question. If cognitive abilities remain completely unaffected, how can we redesign our spaces to let their minds do the running? By truly understanding the exact physiological challenges, whether that's in the brain, the spinal cord, the junction, or the muscle itself, we hold the blueprint to foster genuine empathy, build proper accommodations, and make our world deeply accessible. Thank you so much for joining me on this explainer today. Let's take this knowledge and go build better spaces.